now we proceed with our integral. We know that we're trying to calculate the E field at point P, and we know to do that we have to sum up all the dE P's that we had on the previous board. So let's go ahead and write those. We have to sum up all the ELs times ds over r, e to the j kr minus omega t. Right? And there's the ds. Right? So when you do something like this, when you're integrating with respect to s, because we have a ds there, you're moving up and down in the slit, considering all the different little Haughens wavelets. And you got to think about what here is going to change as you move around in s. Well, the only thing that's going to change is r, right? Because we can really think of r being different for each one of these wavelets. Each one take a slightly different distance to get to p. So we can go ahead and think of the center one as the main one. We'll call that one r. The center one has a value r. So r changes a small amount. This is the weird part of this calculation, okay? R does change in this integral when you change s, but it doesn't change by much. And what that means is it'll affect some terms and it won't affect other terms, okay? So remember, the screen is really far away. The screen is far away compared to the width of the slit and the wavelength. So since it's far away, the change in r is small. So the amplitude is not affected very much. For the amplitude, we're going to treat that as a constant r. And we'll just put in the one for the middle of the slit. However, here, it's going to matter. This is the phase of a sinusoid, and we're multiplying r by 2 pi over the wavelength, okay? So even if the change is small, if it's big compared to the wavelength, then it makes a big difference. And the wavelength is only half a micron when you're doing this with visible light. So small changes in r can matter a lot here, or can matter a lot here and don't matter much here, okay? So to deal with that, here's what we're going to do. I'm going to say, let's go ahead and pull the EL over r out of the integral. That's the constant r. That's the one where the change doesn't matter much. Integral of e to the j kr minus omega t. Now we're going to deal with this r changing. So what we're going to do is just leave that r there and say that corresponds to the center one and figure out what is the difference for all the others. And then it would really just be that r plus the difference. So we'll add that as another term here, k times something else. Okay, so what is the difference? Well, then it's just like an interference problem. We draw a normal like that. We say, as we move up and down, we're at different distances or positions s. So the hypotenuse is s. So we call this angle theta. So this part is s sine theta. So that distance, that extra distance we have to add to r is s sine theta. That's essentially our phase term. That is the term that will consider the differences in phase of all these Haughens wavelets as they make their way down. And then ds is along for the ride. Well, then you look at it, you can say, well, now actually, so if we're saying this is just the r of the middle, this whole thing can come out. So then it's equal to E L over r, e to the j kr minus omega t, and the integral is now down to just the integral of e to the j ks sine theta ds, and as we integrate, we're going to go from minus b over 2 to b over 2. When we add up all these ds's, go from the bottom of the slit minus b over 2, top of the slit b over 2. And then we've got everything that depends on s inside the integral. And we're just going to take this integral with respect to s. And you may be worried about the theta. If you're really observant, you'd say, well, theta changes, right, as you move around. But actually it doesn't. The way we defined it, we also said, just like r, the theta is the theta of this ray from the zero. As we move up and down, we're talking about the differences, and they're all based on that same angle theta. So you don't have to worry about the angle theta changing. It doesn't change very much at all. So let's now take this integral, all the constant parts, E L over r, e to the j kr minus omega t. And if we integrate, we just divide by j k sine theta, 1 over j k sine theta, because we're essentially integrating just e to the x. So you divide by the derivative of this with respect to x. So divide by that, and then you're left since it's just an exponential with the original j, k, s, it's hard to get that s in there, s sine theta, evaluated from minus b over 2 to b over 2. Okay. And then we can go ahead and evaluate it. At the limits, we can say this is equal to e L over r e to the j kr minus omega t 1 over j k sine theta without the s, and then times, and we're going to plug in the b over 2 for s, e to the j k b sine theta over 2, the whole thing over 2, not just the sine theta, minus e to the minus j k b sine theta over 2. And that's far enough for this board.